Okay, hello everyone. Welcome to the presentation. Thanks for the invitation from SSO Task Force and Professor Lin Fan, and it is of great pleasure to present our work in last year based on the collaboration with Dr. Xiaoliang from State Grid Corporation of China, Beijing, and this is Dr. Zhen from Beijing Institute of Technology, Beijing, China. This is my PhD student, Bing Liu. And today our topic is oscillation suppression method based on the accurate control locating. Actually, our work is motivated by the famous incident in Hami, China in 2015, where there occurred sub and super synchronous oscillation at around 20 Hz and 80 Hz respectively. At the same time, the thermal plants several hundred miles away were tripped off due to the induced sharp torsional vibration. As a result, the transfer power dropped from 4,500 megawatt to 3,000 megawatt. The grid station, the grid structure in the right up corner can be simplified to the lower left figure, which consists of PMS wind farm, thermal generator, and sending end AC grid. All of the power is derived by LCC HVD to the remote AC grid. In order to thoroughly analyze the behavior, plenty of research work have been done on the incident in Hami, most of which were based on impedance-based modeling and the related Nyquist variant analysis. However, the limitation of impedance-based analysis is obvious. First of all, as we can see, impedance-based method is a black box method describing the electrical characteristics externally, so as to be hard to establish a relationship between the external impedance characteristics and the internal controllers, arousing the first question, which subsystem should be optimized. Secondly, each subsystem involves multiple controllers, so that it is hard to determine the influence of each controller on the impedance, arousing the second question, that is, which controller need to be optimized. Thirdly, it is hard to determine the optimized controller in the oscillation suppression method. Okay, this is the outline. We will proceed how to identify the dominant controller regarding the oscillation frequency. Okay, so again, our research is based on the Hami incident, whose equivalence system is first simplified to the electrical circuit. According to the grid connection characteristics, each system can be equivalent to voltage sources or current sources, and the whole four-pole system can be simplified as shown in the right figure, where the wind farm and the LCC HVD is equivalent to the current source, and the sending end AC grid and the thermal generator equivalent to the voltage sources. Overall, the stability analysis can be carried out based on the impedance ratios, that is YO versus YS, which should satisfy the GMC. As previously stated, impedance modeling provides the external characteristics aggregating all the dynamics of controller, generator, pyrotronic circuit together. Inspired by this limitation, the sensitivity method is applied to impedance method analysis. Here, take the PMS-WT as an example. Stability of grid-connected PMS-WT system with MIMO, that's a multiple input and multiple output characteristic, depends on the eigenvalue, that's a lambda I over impedance ratio, Y PMS versus Y grid, where the eigenvalues can be represented by the controller parameter as in this equation. Therefore, the sensitivity, which is the first order derivative of lambda I over one certain parameter, can reflect the influence of one certain parameters. The figure shows at the bottom of this slide shows the sensitivity of PLL parameter to the eigenvalues, where the magnitude of sensitivity indicates the influence level change with PLL bandwidth, as we can see in the bottom of the figures. With the changeable PLL bandwidth, the influence band is also varies as well. Okay. According to the previous sensitivity analysis, the corresponding impedance curve can be further derived, as we can see when PLL bandwidth change, the position of resonant peaks in the impedance curve changes as well, and fixed at F1 minus FTSC and F1 plus FIC, where FTC is the PLL bandwidth. Therefore, the influencing bandwidth of PLL can be determined from F1 minus FTC to F1 plus FTC. Similarly, the influencing band of GSC current loop located at two positions range from 0 to F1 minus FTC and F1 plus FTC to F1 plus FIC respectively. Okay, based on the sensitivity method, the influencing frequency band of PMS WT controller can be obtained by eigenvalue sensitivity analysis involving GSC PLL, voltage loop, and current loop, as well as MS power loop and current loop, which is symmetrically distributed alongside line frequency F1 in the figure. Therefore, it can be summarized that the influence frequency band of GSC controller, which involves PLL, voltage loop, and current loop, is determined by its bandwidth. The influence frequency band of MSC controllers, which consists of power loop and current loop, is the same as the GSC voltage loop. Okay, so with the previous effort, the dominant controller can be accordingly determined whether the oscillating frequency is located in the corresponding influencing band or not. Inspired by such criteria, we can develop the oscillation suppression method. At first, we get a stability margin requirement. Secondly, the dominant subsystem of the current source system in the oscillation frequency band by comparing the impedance magnitudes. Thirdly, the dominant controller is determined based on the controller's frequency band. Fourthly, the controller parameters are suitably modified to satisfy the margin requirement as shown in this workflow. In order to verify our analysis and suppression method, one case is studied within 1 second to 8 seconds as a short current ratio of the sending end degree is 10. The system is stable as shown in the in your left figure. At 8 seconds, as you change to 8, system oscillates at 272 Hz and 172 Hz at AC side, and 222 Hz at DC side as shown in the FFT result in the right figure. Okay, to suppress oscillation, the dominant subsystem can be determined by drawing the overall system impedance curves that is drawn in blue in the left figure, and the LCC, HVDC, and wind farm impedance curves as well, which is plotted in dash red and dash green. At the oscillation frequency 222 Hz, the overall impedance actually is dependent on both the LCC, HVDC, and wind farm, so that these two subsystems are dominant at 72 Hz. Subsequently, based on the sensitivity analysis, the GSC of wind farm is dominant at such frequencies band. That's the procedure how to determine the dominant controller. Based on the result of dominant controller, the GS parameter of current loop in PMS GWT is modified accordingly so that the system converge under small disturbance. Sending end is degree SER changed from 10 to 8, which further verifies the effectiveness of the proposed method. Okay, I demonstrate the major dominant controller influencing the oscillation behavior at one certain frequency can be accurately determined so as to suppress the oscillation. This talk can be accordingly concluded as follows. The impedance-based method is suitable for the analysis of large-scale power system, but the black box characteristics of impedance-based method bring out the difficulty of determining the optimized controller. We may find the dominant subsystem and the dominant controller through the oscillation suppression method proposed in these slides in this presentation based on the accurate controller locating. Okay, that's all for today. Thank you very much.